So let's continue our discussion around power series. So power series, part 2. Here we're going to look at power series term by term using derivatives. That is, we're going to find our power series term by term using derivatives. So previously, we found the derivative of power series. This next example is a little different. Here we use derivatives to find the coefficients. Example 1. Find a power series representation for f of x equal to sine x. So here we're going to assume that there is a power series representation, and given that assumption, show that it is indeed the case. We'll also have to assume something about where that power series will converge. Later on, we will prove that this is a legitimate assumption, but so far, we're just going to kind of go with it and see how far these simple assumptions can take us. So let's start here. Let's suppose that there is a power series representation. That is, let's suppose that sine x is equal to some power series c naught plus c1x plus c2x squared plus c3 x cubed plus dot, 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 dot. And so if this is going to be the case, this must be true for all x's. So this is true, or if true, then true for all x. And specifically, we say if it's true for all x's, it must be true at x equals 0. So if x equals 0, then the left side of this, the sine x here, will equal the sine of 0 or 0. And the right side, which is all of this garbage, will equal c naught plus c1 times 0 plus c2 times 0 plus dot, 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 dot. Multiply by 0 a whole bunch of times, you're going to get 0. And so at the end of the day, we just simply have that c naught equals 0. That is to say, we found the first of our coefficients in our sine series, and it's 0. Well, that works so well with sine, we think, what other function might also be easy to evaluate at 0? And we think to ourselves, maybe cosine. So what's the relationship between sine and cosine? They're derivatives. So next up, let's differentiate both sides. Differentiate both sides. So if we differentiate the yellow side, we're going to get the derivative of sine is cosine of x. And the derivative of the blue stuff, of the power series on the right, is going to be derivative of c naught is 0. So we're just going to have c1 plus 2c2x plus 3c3x squared. And then it would be plus 4c4x cubed, et cetera, et cetera. So we differentiated. And when we differentiated, our left side, derivative of sine is cosine. The derivative of the power series on the right is this new power series. Once again, we can evaluate at x equals 0. So if x equals 0, that left side is going to be cosine of 0, which is 1. And the right side is going to be c1 plus 0 plus 0 plus dot, 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 dot. So here's that C1 on the right side. Here's the 1 on the left. And so we have found our second coefficient. So far we found the coefficient C0 equals 0. Now we found the coefficient C1 equals 1. Okay. We found two coefficients out of the infinite number of coefficients. I guess we're sort of better off than we were before. Let's just keep going and see what happens using that same technique. So we're going to play the same game as before. So we're going to differentiate both sides. Oops. Sorry, I'm using a new stylus today. So we're going to differentiate both sides with respect to x. And so we see that the derivative of cosine is negative sine x. Oh, that's an ugly. That's negative sine x. And the derivative of the right side, so this is our derivative, is negative sine. On the right side, we will have, it looks like 2c2 plus 6 c3x plus, looks like we have 12 c4x squared plus dot, 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 dot. Okay. Again, this must be true at all x's. So in particular, if x equals 0, then that tells us if we evaluate on the left, then negative sine of 0 will be 0. And on the right, we will have 2c2 plus 0. Let's see if we can get our colors in place. There's that. There's that. There's that. And from this, it should be clear that we get that C2 equals 0. Okay. Well, now we have three coefficients. Two of them are 0, and we've also found that C1 is 1. Works so well. Let's do it again. So if we do this again, we can differentiate. Oops. All right, we can differentiate. And when we differentiate, the derivative of the left side, negative sine, will be negative cosine x. And on the right side, we will have, looks like 6 c3 plus 24 c4x plus, just, I know that the next term out would be 60 c5x squared plus dot, 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 dot. You may say, where's the 60 come from? You can add some extra terms and see that for yourself. You see the pattern. So our pattern says we then let x equal 0. Then that's going to tell us that the cosine of 0 is 1. So negative cosine 0 would be negative 1 equal to 6 c3, which tells us that c3 equals 1 over 6. Notice that 1 over 6 is the same thing as 1 over 3 times 2 times 1. Okay. So let's see if we can put this together and recognize the pattern of what we've come up with. So we have found, so to date, we've found that C naught equals 0. We found that C1 is 1, C2 equals 0, and C3 equals 1 over 6 or 1 over 3 factorial. Okay, and when you see that factorial show up here, it could cause you to think back to the C1 term, and so 1 would be the same as 1 over 1 factorial. Okay, so let's see if we can put this together. So that tells us that so far, sine of x is equal to C naught is 0. So then we're going to have 1 over 1 factorial, 1 over 1 factorial x, come on, minus, ooh, I lost my minus over here, minus 1 over 3 factorial x cubed. And then we can think about what our pattern is looking like. Our pattern seems to be going, sine of 0, cosine of 0, sine, negative sine of 0, negative cosine of 0, and then it's going to loop back around. So it goes from sine of 0 to cosine of 0, from cosine of 0 to negative sine of 0, from negative sine of 0 to negative cosine of 0, and then it flips back around to the top. So the signs that we're evaluating each time are going to go 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. So that tells us we're only going to have these odd powers, and our signs are going to alternate, and we can see the coefficient, or we can see the factorial showing up. So our next term is going to be plus 5 factorial x to the 5th. Our next one will be 1 over 7 factorial x to the 7th, plus et cetera, et cetera, et cetera. So we could write this more concisely as that sine x is equal to the sum from n equals 0 to infinity of, we got to have alternating signs, so we'll have a negative 1 to the nth power. And then we want to have just odd powers, because notice your powers are 1, 3, 5, and 7. And so we'll have x to the 2n plus 1. So there's that odd power. And similarly, we have odd number factorial, odd number factorial, odd number factorial. And so we'll have a 2n plus 1 factorial in the denominator. So here, gotta be careful. Here is our power series formula for sine x. We haven't yet talked about when that power series is valid, like for what x values it converges. We're going to get that a little bit later on. But we were able to use derivatives to find all the various coefficients. So the series we found is an example of a more general type of power series called a Maclaurin series. So here's our definition. Suppose the function f has derivatives of all orders on an interval centered at x equals 0. Then its Maclaurin series is given by f of x equals f of 0 plus f prime of 0 evaluated x plus f double prime of 0 over 2 factorial times x squared plus the third derivative of f evaluated at 0 over 3 factorial times x cubed plus the fourth derivative of f evaluated at 0 over 4 factorial times x to the fourth plus dot, 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 dot. So what I want you to notice here is that the derivative number matches the factorial, and that all of these are being evaluated at 0. And not only are they being evaluated at 0, but it's the fourth derivative, the fourth factorial, and the fourth power. Like all those things are working together. But this is how we make up the Maclaurin series. I also want to clarify a typo. This is f prime of 0, not f prime of the letter O. So this can be written more concisely as f of x equals the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 over n factorial times x to the n. So you see all those nth derivative, n factorial, x to the n, and all the functions are being evaluated at x equals 0. So note, a Maclaurin series is a type of power series. It's found by finding the coefficients term by term using derivatives. Example 2, find a Maclaurin series that is a power series representation for f of x equal to e to the x. So if you want to find a Maclaurin series, that means you need to find the coefficients. And conveniently enough, it's kind of straightforward. So we know that our coefficients are going to come from derivatives. So C naught is going to equal f of 0 divided by 0 factorial. C1 will equal f prime of 0 divided by 1 factorial. C2 will equal f double prime of 0 divided by 2 factorial. C3 will equal the third derivative evaluated at 0 divided by 3 factorial. C4, fourth derivative evaluated at 0 divided by 4 factorial, etc., etc., etc. Well, this means we need derivatives of f of x, and we need to evaluate them all at 0. Nice part about derivatives of e to the x, I think I said f of x. We need derivatives of e to the x. Nice part about the derivative of e to the x is it's just e to the x. So f of x is e to the x at 0. This will be just 1. So e to the 0 is 1. Divided by 0 factorial, which is 1, or 1. F prime of x is e to the x, evaluated at 0. This is 1. Divided by 1 factorial is 1, or just 1. F double prime of 0 is e to the x, evaluated at 0 is 1. Divided by, here I'll write it as just 2 factorial, or 1/2. The triple prime of f would be e to the x, evaluated at 0 is still 1, divided by 3 factorial. The fourth derivative of f is e to the x, evaluated at 0 is 1. It won't always be this easy, but e to the x is pretty nice, divided by 4 factorial. And I think by this point, we can see our pattern. We can see that if we had a Cn, our Cn would end up being 1 divided by n factorial. So putting this together, we get the e to the x is equal to 1 plus 1x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. Ooh, I think we're seeing a pattern. This would be x to the 4th over 4 factorial plus x to the 5th over 5 factorial, etc., etc. Or in other words, e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. Here is our power series, specifically a Maclaurin series representation for e to the x centered at 0. We've introduced this new centered at 0 vocab. We'll explain it more later, but for the time being, we'll just kind of recite it. So here's our power series, aka Maclaurin series, centered at 0. This particular series may be familiar to you. You may, if you're paying attention, you might remember. This was actually also included in our differential equation solution. So in the solution to f of x equals f prime of x. Come on. Okay, question that was in the previous example. Notice we still haven't addressed the issue of when this power series is valid, like for what x values this will converge. That's going to come later in a future video. So as with geometric series, the Maclaurin series can be manipulated to go quite a ways. So in example 3, find a Maclaurin series that is a power series representation for the following. So in A, we have f of x equals e to the 2x. So let's start by recalling the thing that we're given. So recall that e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. And let's see if we can see this thing in color. So notice this is e to the green x equals the sum from n equals 0 to infinity of green x to the nth power over n factorial. So that should help you see that e to the 2x, or f of x, will have a green 2x. So this will be the sum from n equals 0 to infinity of 2x to the n over n factorial. Now, if you wanted to, you could go through the whole Maclaurin series derivation, but you don't have to. You could save yourself a little bit of time. If you wanted to, you could rewrite this as n equals 0 to infinity of 2 to the n, x to the n over n factorial. So maybe that's a cleaner, prettier way of writing it. And you could actually see where this would come from, because if you started taking derivatives of e to the 2x, you get, f is e to the 2x, f prime is 2 e to the 2x, f double prime is 4 e to the 2x, f triple prime is 8 e to the 2x. The fourth derivative would be 2 to the 4th e to the 2x. The fifth derivative would be 2 to the 5th e to the 2x. Oh wait, those are powers of 2 that are showing up as coefficients. So you can see how this formula would come to be. In part B, we're looking for a power series for g of x equal to x to the 4th e to the x. And so here we can play a different type of little cleverness. And so again, we recall that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. Well, we don't actually care about e to the x. What we care about is x to the 4th times e to the x, which would be x to the 4th times the sum from n equals 0 to infinity times of x to the n over n factorial. And what I want to point out here is that as far as the summation is concerned, the variable is n. The variable isn't x. So the summation thinks the variable is n. The function thinks the variable is x. They're sort of like two separate things. And so as far as the summation is concerned, the variable is n. And so we can bring this x to the fourth inside the summation. So this will be equal to the sum from n equals 0 to infinity of x to the fourth times x to the n over n factorial, or just, let me clean this up a little bit, or just the sum from n equals 0 to infinity of x to the n plus 4 over n factorial. So what these examples show you, I hope, is that just like we could get a lot of mileage out of a single geometric series, so we have one geometric series and we could manipulate it and get a lot of other series. Similarly, we can get a ton of mileage out of a single Maclaurin series. So it's like one little teeny formula gives us a whole bunch of power, and that Maclaurin series concept of taking derivatives and using the derivatives to find the coefficients to find a power series gives us a huge amount of power and potential in this world of power series. Once again, these power series, these are like the duct tape, the Swiss Army knife of mathematics. All right, so one question that students have is, what do we need to memorize? So there's 3 Maclaurin series that I want you to memorize. The first one is the one we've been using from the recently, the e to the x Maclaurin series. The second one I want you to have memorized is the Maclaurin series for sine x that we derived earlier on in the section. And third, I want you to have memorized the cosine Maclaurin series, which you may remember as one of the examples we did back in, I think, the very first lesson, maybe on page 2 of starting to talk about power series. In case you're trying to remember which is which, you can always, substitute in some upper bound and just graph it on your calculator. But it's interesting to note that sine is an odd function. It's symmetric about the origin. And notice that the sine has all of those odd powers of x and odd factorials. So everything about sine is odd. And similarly, cosine is an even function, symmetric about the y-axis. And you can see that all of those factorials, all of those powers are even powers. So it sort of gives you a new meaning of this idea of an odd function and an even function. When you see, oh, an odd function has only odd powers, an even function has only even powers, that's pretty crazy. Continuing on, if you've been paying attention, you may have noticed that we've found power series in the previous few examples, but have not made mention of where these series are valid. This is because we are no longer working with geometric series, and consequently, we need more power. That is a pun. So specifically, to figure out where these series are valid, where they converge, what we're going to later call the interval of convergence, we need 2 facts and 1 method or test. So fact 1 is that the harmonic series diverges. You might say, what is the harmonic series? The harmonic series is the series of the sum of all the 1 over n's. Notice that here we have to start at n equals 0, so we don't divide by 0. Dividing by 0 is undefined. So it diverges, the sum is equal to infinity. What are we saying here? We're saying that 1 plus a half plus a third, plus a fourth, plus a fifth, plus dot, 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 dot. If we add up an infinite number of these fractions, even though they get smaller and smaller and smaller and smaller, this is going to equal infinity. So that's fact number one. You will, at the moment, I'm just stating it as a fact. In a later course, you'll get to see why, or we will prove why this is the case. But at the moment, I'm just telling it to you. I would be happy to take it offline if you want a proof of it. Fact two is that the alternating harmonic series converges, that is, equals a number. In symbols, we would say that the sum from n equals 1 to infinity of -1 raised to the n plus 1 power over n equals a number. It happens to be equal to the ln of 2. The ln of 2 part isn't important. Like, this is not important, at least for our purposes. Important. What is important is that it converges. So what does this mean? This means that, so if I put in n equals 1, I'm going to get a positive 1 out. So it means 1 minus 1/2 plus a third minus a fourth plus a fifth minus a sixth. So you've got the signs are changing, but it's the same series as above, but now the signs are changing. If I continue on in this path forever, I would say that this converges. It equals a number. Okay. So that's fact one and fact two. So why does one infinite series converge and another diverge? That is a big question, and we're going to leave it for another course. However, we can see that sometimes we sum an infinite number of terms and get a number, that is, it converges. And other times we sum an infinite number of terms and we don't get a number, it diverges. One of the most powerful ways of determining if a series will converge is to ask, do the terms decrease fast enough to converge? That's great, but how do we measure fast enough? So in example 4, we're going to explore the ratio of consecutive terms on these three series. So we want to look at the ratio of consecutive terms on these three series, the first of which is 2 times 1/3 to the n. You'll recall that this is a geometric series. Pardon me. It's a geometric series. And it converges. And we've already worked with this. The sum from n equals 0 to infinity would be the leading coefficient, which is, so this is 2, pardon me, gotta get my work together. 2 times 1/3 to the n will be 2 divided by 1 minus 1/3, which works out to be 3. So it converges to 3. But for our purposes, what I want to point out is that this thing is equal to, it looks like 2 plus 2 times 1/3 plus 2 times 1/3 squared plus 2 times 1/3 cubed plus 2 times 1/3 to the 4th plus dot, 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 dot. Okay, so that's what my series looks like. And what I'm going to do is I'm going to look at consecutive terms. So consecutive terms such as, it doesn't matter which ones, but maybe I'll look at these two terms here. And so I'm going to look at the ratio. Ratio means division. So I'm going to look at the ratio of the second of the highlighted terms divided by the first. So look at the ratio. And in this case, the ratio is going to be 2 times 1/3 to the 3rd power divided by 2 times 1/3 to the 2nd power. And notice this ratio is equal to 1/3. Okay, that's great. What if we tried a different combination? What if we looked at the next two terms out, the blue terms? Well, in this case, again, we would look at the ratio of the second term, okay, here. And so our higher power would be a 4 divided by the first term, or the previous term, here, which would have a power 3. And again, you can see in this case, for the second time, the ratio of the two is 1/3. So, and you can see that this would continue on regardless of how far up we went in the series. So what you'll notice is that if we looked at the ratio of an plus 1, and we divided it by an in this case, so in the highlighted case, so if n was equal to 3, that would give you, this is interesting. So I've got to back up on my vocabulary. So an represents the nth term in the sequence. It's sort of like cn, but cn is just the coefficient. So an is the whole term. So in this particular case, again, working on my vocabulary, a naught would be 2, a1 would be 2 times a third, a3 would be 2 times a third squared, a4 would be, I said a1. It would be a naught is 2, a1 is 2 times a third, a2 would be 2 times a third squared, a3 would be 2 times a third cubed, etc., etc. So in this case, the an, like in this particular case, our n would be 3. So a3 would be 2 times a third cubed, and then a n plus 1, n is 3, so a3 plus 1, or a4, would be the 2 times a third to the fourth. And in each of these cases, we got a third. So note what we're saying is that if you look at those consecutive terms, it looks like the yellow one, the later term divided by the earlier one, the green term, okay, has a ratio that's always a third, or specifically it's always less than 1. Okay? And because it's less than 1, that means our series is getting small very, very quickly. They're decreasing by a third, about a third every single time. So that's the A series. Or I should say, example 1, the geometric series. Let's do the same thing with the harmonic series. So if we do the same thing with the harmonic series, notice this is equal to 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, et cetera, et cetera, et cetera. So let's look at some consecutive terms. So if we look at some consecutive terms, say 1/2 and 1/3, and we're going to take the ratio, the second term is going to go in the numerator, 1/3, divided by the first term, in the sequence, 1/2. And altogether, this would be the same as, looks like 2/3. Okay. And then maybe we could look at some later terms. Suppose we look at these green ones. So here, we'll look at the second term, 1/6, and we divide by the first term, 1/5, and this simplifies to 5/6. You could look at this pattern and realize that what's going to happen is as we continue on, we're going to keep going, dot, dot, dot. At some point, we're going to have a 1/n plus a 1/n plus 1 plus dot, 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 dot. And so if we looked at those terms, you could see that you would get 1 over n plus 1, 1 over n plus 1 divided by 1 over n, which is equal to n over n plus 1. And notice that as n goes to infinity, n over n plus 1 equals 1. So that tells what that tells us is that our terms are not decreasing fast enough for us to know, using this approach, whether or not the series will converge or diverge. We happen to know that this particular one diverges. We could do this same thing on the alternating harmonic series, and it would also equal 1, but we would know it actually might equal -1, but it would converge. And so you can see that if it equals 1, sometimes it converges, sometimes it diverges. It's not going to converge fast enough for us to have the kind of information that we want. So in C, again, we're trying to understand something about how fast a series, like how fast the terms in a series shrink. So we can write out some of these terms, pardon me. Okay. So here we actually have a power series with x's involved. And so this will be like 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus dot, 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 dot. And again, we could ask what happens if we look at the ratio of consecutive terms. That is, how fast are these terms approaching 0? So if we looked at those first 2 terms, we would take the top term, x cubed over 3 factorial, and divide by x squared over 2 factorial. And this is going to equal x over 3. Or maybe we could look at the x to the 5th and x to the 6th terms. Here, this would give us x to the 6th over 6 factorial divided by x to the 5th over 5 factorial, which simplifies to x over 6. And so I think it should be reasonable to see that if we continue this out, we plus dot, 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 eventually we're going to get to an x to the n over n factorial plus x to the n plus 1 over n plus 1 factorial plus dot, 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 dot. And so if we looked at those 2 terms together, we would have x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial, which simplifies to x over n plus 1. This stuff up here is from a previous example. And what I want you to see here is that as n goes to infinity, as long as x stays fixed for a fixed value of x, we know that x over n plus 1 will go to 0. That is, once again, the consecutive terms get smaller and smaller and smaller. They shrink very, very rapidly relative to each other. The ratio of the two gets smaller and smaller very, very fast. And so when they shrink quickly, when this ratio goes to a number less than 1, we're going to get convergence. When this ratio is 1, it's going to be inconclusive. It can kind of go either way. When the ratio is greater than 1, we're going to get that's going to diverge. And this is a little bit of an exploration of a concept or a test that we're going to call the ratio test, which we will introduce in the next section. So what we've done in this brief lesson is we've introduced the idea of a Maclaurin series, and then we've started to talk about how we can get hints of whether a series converges or diverges. And we've done that by introducing two facts, first about the harmonic series, the second about the alternating harmonic series. Harmonic series diverges, alternating harmonic series converges. And then we've talked about this idea of series converging if the terms get small fast enough. That is, if the ratios of the ratio of consecutive terms is small. That's how you would know if something decreases. And we measure that by looking at the ratio of the consecutive terms and asking, is that ratio less than 1 for less than 1 as n gets very large, as we look at a large number of terms. There's a lot of unknowns here, not the least of which is, what if that ratio is negative? Does that mean it's less than 1? Does that work? And we will address some of those unknowns and try to solidify this into what's called the ratio test in our next lesson. For the meantime, hope you're enjoying yourself with power series as much as I am. Have a wonderful day, and I'll talk to you in the next lesson.